Okay, so last time we were together, we talked about filters. We talked about the four different types of filters, two basic filters and two derived filters. The basic filters, low pass filter and the high pass filter, and then the derived filters, the band pass filter and the band stop filter. The band stop filter is also called a notch filter. We talked about filter action. If you weren't present for that lecture, none of this will probably make, well, you can actually do the math and the analysis, but if you really want to understand how filters work, you got to go back and look at that lecture to understand what we call filter action. Now, filter action, there are many kind of filters. Filters are composed of resistors and then reactive elements. So I'll have an R, an L, and a C part in any combination. I might have an R, L, C. I might have an R and an L. I might have an R and a C. Different styles, different combinations, different designs. What we learned about was the RC filter because it's a simple filter to understand. And then filter action as applies to an RC circuit, we talked about that. The fact that for high frequencies, the capacitor acts like a short. For low frequencies, the capacitor acts like an open. We call that filter action. We applied that to the two basic filters to help us understand how they work. How is it that they filter? Filters separate frequencies. So how is that achieved? And filter action helped us to understand that. We understand that the band pass filter, the band stop filter are basically combinations of the basic low pass and high pass filter. So we looked at that. Now, for every filter, there is a frequency response curve, And we looked at two last time. We looked at the ideal curve, and we looked at the practical curve, the actual curve. So the ideal curve is that if I had a perfect filter, if God made a filter and was perfect, this is how we would like it to behave. So we went through for the low pass, for the high pass, we looked at the ideal curve, and then we compared it to the actual curve. And then we did kind of a high-level problem. We worked through an application. It was an audio application where we have a problem that we have this thing called a speaker, and the speaker has a certain bandwidth, and the bandwidth of the signals is way wider than the speaker, one single speaker can handle. So what we did, we said, all right, maybe we can divide this bandwidth up into chunks, the bandwidth being human audio bandwidth. And instead of using one speaker, we'll use three speakers that have different bandwidths, one for the lows, one for the mids, one for the highs. And we just kind of thought through it to see, well, how would we connect things up? What kind of filters would I need to get an audio system to work and have what you might call high fidelity? So we worked through that. And in that, we learned how to put those graphs together. And we learned a new term, the crossover point. When you move from one part of the frequency to another, from one speaker to another, you want one to pick up where the other leaves off. And so they cross over at that point. And the graphs actually make that crossover. So the term crossover point, if you're familiar from audio, that's where the term is derived. That's where it comes from the actual graph. So what we did not do is an analysis. So I want to do that. I want to do an analysis. And if you got a chance to look at the document that I put on Blackboard, this is going to take us through some filter analysis, and then your quiz. I don't know. I got to go back and look at the recordings to kind of see where we are on quizzes, but we need to do some work on filter analysis. So we're going to keep it simple, keep it basic, and keep it kind of short, and we'll go into filter analysis. That's what we'll do today. Before we do that, I want to mention, well, you realize now I am up at the school. I did actually do a lab with my other class yesterday. So we were able to do a lab. Now you guys are lucky because you get to come into the campus. They wouldn't let them come in. So what I had to do is project the lab on the board. But the beauty of it is I can actually focus the camera on the board. They could connect stuff up. It's just a basic lab, so they can do the stuff at home. So I have the ability to do labs. So you guys are actually going to come in. I've scheduled with the school that you'll come in next week. So this will be the last camera meeting that we'll have. And after this, we'll do face-to-face. We only have next week. And so you'll come in on Monday. The time I set up, I was trying to get, first choice, I'd like to have an off day. That way I can keep lecturing and cover some of the other points. But it turns out that not every student was able to meet on a day that we're not scheduled to meet for class. So that limited me to Mondays and Wednesdays. And then I had a couple students that had some time restrictions on Mondays and Wednesdays. So I ended up setting it up for, I believe, 2:30 to 4:30. So what we'll do is we'll meet Monday. Now, I don't know. I guess I'll find out tomorrow. Or I know there's some things where you need a mask. So please bring a mask with you. I don't know if I have any. I may have some extra ones at my house. I'll check. But you want to bring some kind of face covering. I don't know. I have to see. They sent an email out to the guy that's on the safety committee that made this possible. They may want to take your temperature when you get here. We just have to see. But as I get information, I will send that information to you. So just expect to be here. Now, if for some reason you can't make it, you got to let me know. We'll see what else we can work out. Some kind of way, you have to get your hands on the oscilloscope, even if it's just one time. So my plans are to come in. We'll do a basic equipment review. There's some equipment that we need to talk about to be able to do the AC lab, and that's called a function generator. And then there's two types of oscilloscopes. We have an analog scope and a digital scope. So I set one day aside to do analog stuff. And the second one is kind of a self-paced lab where you kind of can go through yourself. It's a really nice tutorial I have, and you'll do that lab, and that'll be it. Between now and then, there is another video lab that you'll do. You did one or two of those for me already. But this one is on the oscilloscope, and it just deals with some of the basic terms for oscilloscope. So I'll put that out as soon as I can get it out. I'm just really, really bombarded between doing stuff remote, trying to keep up grades and everything. I'm trying my best to stay afloat. So as soon as I can get that out, I'll get it out. Easy to do. I think there's 20 terms, if I'm not mistaken. You go through. There's this video that'll, if you have trouble sleeping, just watch the video I'm going to give you. You'll go to sleep real fast. You'd probably rather watch paint dry than watch the video. The guy, there's two guys in there, and they go through the oscilloscope, but they tell a lot of what I want you to know about the different points and terminology that apply to the analog oscilloscope. So, but feel free to use that video or any one you want to get the answers for the lab. So the format is as a handout. I think there's 2 pages with some terms on it. You just watch either that video or you Google and you find out what these terms mean or what they do. You write it down, you send me that back, and you got credit for the video lab. I want you to do that before you put your hands on the oscilloscope. So that's the plan for next week. And between now and then, I may have some other side assignments you do. Now, as far as the material not covered, what I'm probably not going to, I might be able to do some things while you're here, but I'm thinking the lab might take all the time. So I was talking to Jacob at one point, and he mentioned, what about making a video of some of the stuff that I'm not going to talk about? So what I'm not going to talk about would be with superposition, which you can still do that. I still might assign that because you know how to do superposition. It's just a matter of doing it with AC. So that's not a big deal. You can almost do that without a lecture. Thevenin's theorem of maximum power transfer, although you can do it without a lecture, I kind of like to talk about it just to remind you. To me, that's really important. So I could possibly do that as a video and just you watch it at your leisure. And then this thing about 3-phase, I don't feel bad at all about, because I think I've been here since what? I've been here for 13, this is going to my 14th year employed here at Cincinnati State. And I think in 14 years, I think I didn't teach AC the first year. So in 13 years of teaching AC, I think I might have gotten the 3-phase power 2 or 3 times at the most. So, and maybe a few times I just barely skimmed the surface because we have more material in this course than we do time. So, is it important? Well, everything's important to me. Anything but if you are power systems, then yeah, it's important. You will definitely get that in your power systems classes. If you're not power systems, it's more interesting than important. So depending on how things go, I may or may not do a video of that. What would be a good idea is to just do a video anyway, since I hardly ever get to it, and that way, even when we meet face to face, we can watch the video if I don't have enough time to get it. But anyway, I don't want to use up all the time talking. Just make sure you follow, look at Blackboard to see if I send out announcements between now and Monday. And then Monday, plan to meet at the campus. And I'll let you know if there's any special things you need to do other than the face mask. Probably we'll meet at the loading dock, and then you guys will come in that way. But I'll keep in contact with you between now and Monday. So before I start, does anyone have any questions for me? Okay, well, what I want to do today is talk about filter analysis.
I had a question.
Okay, Sam, go ahead.
On the sheets that you gave, there's just one that just says part 1, but I couldn't find any like part 2 or anything like that. Was that as intended?
I didn't send you part 2. Part 2 is more of the same of what's on part 1.
Okay,
so,
I was just double checking.
I don't have time to do part 2. If you want part 2, I can give it to you. You can still do it. I don't care if you do it. But it's just more practice problems. So there's a part 1. I created a part 1 and part 2. And I didn't put up part 2 because I knew we weren't going to get to it. Today is going to be it for the lecture. And then I had a doctor's appointment, so our time is even cut shorter. So I thought about on Monday, but we really got to get our hands on the O-scope. So between working with the O-scope and going over part 2 of this, I think the O-scope is way, way more important. So it's just more of the same kind of thing. If you look at the sheet for today, there's a total of 6 problems. 3 really, really basic problems. And then the last 3 are not particularly hard, but they really kind of drive home the principles and the points that I'm making about filters. So this covers everything that I want to do. Part 2 just gave you more of kind of the same thing. So probably should have took off the part 1 so you feel complete. So it'll be okay. Now, before we get into filter analysis, let me talk about frequencies and bandwidths. When we deal with frequencies and bandwidths, you know that they can be quite huge. They can be pretty big, or I should say the bandwidth can be pretty wide. And what I'm saying is, go back to the example that we gave you the other day. We gave remember the audio example we gave? Let's go back to that for a second. The bandwidth for human hearing on the low end is 20 hertz, and on the high end is 21,000 hertz. And just to make it simple, since we're only 20 hertz away from 0, let's just start it at 0 so this graphs nicely. So I want to start it at 0 hertz. What if I want to make a graph? Now, we looked at graphs last time called frequency response curves. They're also called bold plots, by the way. I don't know if I mentioned that. Bold or boldy. I think it's bold plots is the way I hear most people say it. I don't like that. I think frequency response curve is harder to say, but it says exactly what it is. And this thing must be a person's last name or something. I don't know. But sometimes you'll hear a person talk about a bold plot. All they mean is a frequency response curve. But anyway, most of the time you deal with bandwidth, the number of frequencies from 0 to whatever is huge. I think we did one analysis, one of our practice problems, and one of our sheets that we did, there was a bandwidth of 400 or less. And I'm telling you that with a narrow bandwidth like that, that's only in textbooks, because in reality, unless you're transmitting just a tone, or maybe the remote control for your TV set where you just have a narrow number of functions you want to do, you may be able to use a narrow bandwidth for that. But in most cases, your bandwidth needs to be way wider than that to do anything. I mean, just consider the case of TV. In TV, when you transmit a TV signal, now I'm not talking about through cable TV. I'm talking about the old TV where you just use wire, the antenna on your TV. You have three signals. You have a picture, and that picture is transmitted in AM, amplitude modulation. You have sound, and the sound is transmitted in FM. So for sound, you got to fit this bandwidth in there because it's for human hearing. And I have no idea how much bandwidth you need for picture. I would assume a whole lot. For color TV, you got the picture information and the color information. So this bandwidth is probably huge. And on top of that, you got another signal that you transmit called the sync signal. And the sync signal is responsible for making sure that the picture and sound arrive when they're supposed to, so you don't have a guy's mouth moving and then a few seconds later the words come. So they keep them together. So just for like basic TV, the bandwidth is like ungodly huge. So my point is that most of the time you deal with bandwidth, and not all, but I'm fair to say most applications, you need a lot of room, a lot of space. Having said that, what does that do for graphs? What if you want to make a graph of this one, of the audio frequency? Let's say we make a graph of that. Think about what your graph would look like. You got two choices. You got to graph a number from 0 to 21,000. So one thing you can do is you could, if I start out at 21,000 right here, I can start over here at 0, and I can put 21,000 tick marks there. And I'm being silly right now. I can put 21,000 tick marks there, and that would take forever, and they would be so close together you couldn't see what was going on. That's one option I have. The second option I have is, all right, let's just make a real graph. So maybe I can actually make the tick marks really wide, enough for me to see them, all the way over to 21,000. If I start this at 0, but if I do that now, I don't know if you guys know where I am. I'm in room 206. That's where we'll have lab in room 206, right across from the tech center. So I'm pointing over that way. There's a window, and over that way there's some equipment. So at the window, I can look outside and I can see the front circle of where the flag is. It says Cincinnati State. If I made this graph with 21,000 tick marks, this horizontal axis, I would have to extend out the window, down the driveway, probably past the flagpole to fit all 21,000 tick marks in there to make my graph. Neither one of those options really works if you think about it. Both of them are nearly impossible to do. So how is it that I can show a graph? How would I really make a frequency response curve when most of the numbers we deal with, when we deal with a concept like bandwidth, I have such a wide range in numbers? Well, here's what they do. They use something called a logarithmic scale, or log scale. Now, I should have put some, I'm sorry I didn't put this on black. I actually have a piece of a semi-log paper. You may know what that is from your math class, but I'll just show you. But I actually have you can Google semi-log paper. If you Google it and get a picture, here's what you'll see. You'll see that these tick marks are here. So mine start like that, and then like that, and then like that, and then like that. And as you go further out, they get closer to each other. And then there'll be a line like right here. And then it'll start out again, wide, closer, closer, closer. And then there'll be a line right here. And it keeps doing that. Starts out wide, wide, closer, closer. And then there's a line right here. So this would be the log scale. And over here, it's just a linear scale. So these will be evenly spaced. So that's the linear scale. And when you have the graph paper like that, it's called semi-log paper. Back in the old days, before calculators and all the technology you guys have, like when I was in grade school, we used this semi-log paper. So this is a logarithmic scale where when I move from left to right, the tick marks get closer and closer and closer and closer. Over here is a linear scale, but there's no reason why you have a log scale here and a log scale here. Well, then it will be called log paper. Instead of semi-log paper, it's log paper. Now, that's not very good to work with because it's a little hard to see what's going on. But think about what happens if I have, say I had this. Basically what this does is by making the tick marks closer and closer and closer together as we move from left to right, what you're doing is, imagine that I have a linear scale. So I got a linear scale. So these tick marks are evenly spaced. And let's say I make a graph of something. Now, I could not use the semi-log paper if I had a lot of changes in my graph. Here's what I'm saying. Let's say my graph did this. Let's say my graph did that. If I took this linear scale and I turned it into a log scale by pulling this back to make some of these tick marks get closer and closer together, that would kind of deform it would deform the graph. And so it'll as I pull it back, the graph will be deformed. And I'll actually lose information. I can't see what's clearly going on with the graph. So in the case where I have a lot of change going on in my graph, it wouldn't be proper to use a log scale. Fortunately, when we deal with bandwidth, especially with audio and things like that, this is not the kind of graph I have. I might have a graph like this. Maybe I have the graph for a band pass filter, and maybe it's for the audio spectrum. So maybe I have a graph. What does the graph for a band pass filter look like? Well, what we learned the other day is it starts off like this, it goes over, and then comes down. And maybe this might be 10 hertz, and this might be 20,000 hertz. Now, the point I'm trying to get across to you is right here, there's nothing changing here. It's pretty much constant. There's no variations in the top of the scale, the height of it. Since that's the case, if I could pull the scale back to make some of these tick marks get closer than others, so it looks like this, then the scale will be compressed. The scale will be compressed, but it won't distort the graph because there's nothing changing in there. So when we do frequency response curves, typically, almost always, they use semi-log scales. They use a semi-log paper. Log for the frequency and a linear scale for amplitude or whatever this vertical scale is going to either be voltage, current, or something called gain, which we'll talk about today. So if I can remember, I'll put up an example of some log paper, semi-log paper on Blackboard, maybe when I'm done, or just go to Google or YouTube and just Google semi-log example, and you'll see how these, when you move from one part to another, one decade to another, one part to another, they get closer and closer and closer and closer. And if you guys imagine that if I start off with a linear scale, it was some way for me to make this into a log scale while the graph is on it, then I would shrink the scale, I would shrink the graph so I can fit a number from 0 to 21,000. I can still fit it on the graph without losing valuable information in the graph. And the only reason I can do that is because there's not anything changing as I go from 10 hertz up to 20,000 hertz or whatever the bandwidth is. And so we use a logarithmic scale when we do frequency response curves. Well, since we use logarithmic scales, we can't use regular, when we do the math, what kind of, a logarithm is what? A logarithm is just it's kind of like a fancy exponent. And so since we use a logarithmic scale to represent frequencies or frequency response curves, we deal with something, we got to deal with logs and logarithms and exponents and all that kind of math. And so what they came up with was a unit that works well on the log scale. The unit is called a bell. A bell. And a bell is an actual unit. I don't know if it's an engineering unit or a math unit, but a bell is a unit that actually deals with exponential and logarithmic type numbers. And usually when we use this log paper, it's based on tens or decades. So this is a decade, this is a decade. So decade. So we base 10 is the decimal. We use the decimal system. It's a base 10 system. So they add the word deci here, and that just means 10. And bell is kind of a log or exponential type of a number. And so they put these together, and the word that they get is decibel or decibel. And so you might have seen that unit before. It's a unit where you compare powers together using a ratio, the decibel. And so what they'll do is they'll write this either like a lowercase d and an uppercase b, or I've seen it like a lowercase d and a lowercase b. They shorten this decibel to dB. And so when we do analysis with filters, since we use a logarithmic scale, the math that fits with that is the decibel. So it's a unit, and it's a unit comparing powers to each other. Now I'll get to the decibel in just a second. I want to talk about this idea of gain. I mentioned gain in last class, and I want to bring it out here, and then we'll come back to the decibel. So let's talk about gain. I'm going to get rid of this because I might want to refer to that graph again. So in electronics, when you go to more advanced courses, if you notice, when we made graphs a couple times, I think when we did resonance, filters, I mentioned the fact that here we might have frequency on this axis or time, but here we're going to have voltage, we can have current, but there's also a quantity called gain. And some books use a G for gain. I'm not. All the books I've ever learned in use an A. I don't know why A, but they use an A for gain. So I don't know what your book does. I'm going to use an A for gain. Now, what is gain? Well, all gain is comparing an output quantity and an input quantity by the process of division using the ratio. So gain, in general, gain, I take an output quantity and I divide it by the input quantity. And that gives me my gain. Now, depending on what output quantity and input quantity you use, it's how you name the gain. So here's what I'm saying. Let's say I'm using voltage. So if I want to know voltage gain, what I'll do, the gain will be the output voltage divided by the input voltage. And so I would call this A, and I would subscript it with a V, because that's voltage gain. I can have a gain like this, where I have a gain, and I take the output current divided by the input current. In that case, this would be an I there. That's a current gain. Or maybe this is more typical. I have a gain where I'm taking the output power divided by the input power. In that case, that's a power gain. Now, when we do our definition for decibels, it's based on this idea of power gain. This right here. Power gain. So decibels, the dB, is based on that kind of gain. Now, what can gain tell us? What does gain tell us? Well, remember we talked about amplification and magnification? There's a difference. A difference between amplification and magnification. Can a step up, well, what is amplification? Some people will say you put in a small signal and you get out a bigger signal. Well, what kind of signal? You mean voltage or current? Yeah, that's what I mean. Well, no, that's not amplification. That's magnification. If you put in a small signal and get out a larger signal, but the power in and power out are not the same, or are they the same, then you have amplification. A step-up transformer gives you, I said that wrong. A step-up transformer gives you magnification. You can put a small voltage in and step it up, but that comes at the expense of the current. It goes down. And in an ideal transformer, the power you put in is equal to the power you put out. So that's not true amplification. I'll keep getting that back. That's not true amplification. It's magnification. You're magnifying or making bigger the voltage or current. True gain means you have an input increase in power. So I start out with a small amount of power and I get out a large amount of power. So there must be, for true gain to take place, true amplification, you must have an increase in power. It doesn't matter what the voltage and current are doing. If there's not an increase in power, then you don't have amplification. So the gain can tell us if we have amplification or if we have something called attenuation. In other words, you can think of it like this. If I have a gain greater than 1, then I have amplification. If I have gain less than 1, then I have, I don't know if I can spell that. Let me try it. I think that's attenuation, but let me look on my sheet because I'm a terrible speller. And this is usually when Jason or Jacob chimes in and say, hey, you're missing this letter. But I screwed it up. So attenuation and that means you have a decrease in signal. Now, when I was in college, I was kind of embarrassed because my spelling was just terrible. I couldn't spell worth a quarter. I would be embarrassed about it. But then I stopped being embarrassed because the people that could spell couldn't do calculus and calculus-based physics and all that stuff. So I said, well, I'm not embarrassed anymore. Anyway, gain is important. I can have a gain greater than 1. I can have a gain less than 1. This is not amplification. Negative amplification is attenuation. That means my signal is getting smaller. I can even have a gain equal to 1. And that means there's no amplification or attenuation. I'm not going to go into that, but if you take your electronics course, there's reasons why you would want to do that. There's certain amplifiers that don't really amplify. They actually have a gain of 1. If you want to know more about that, you can ask me off camera, and when we have more time, I can dig into that a little bit with you. I don't mind. So now you know gain, output quantity over an input quantity. Well, there's 2 ways you can express all of these gains: the regular gain and then the dB gain. So like let me erase this, and I say, all right, well, what's this? You can say A is gain. Well, what kind of gain? Okay, well, maybe I put a P here. So it's power gain. But I can also have that power gain written in dB. And so I can subscript to subscript, which you really can't do too well on a computer. You can't so when I took this, we would subscript to subscript. The subscript to subscript would be the dB. So since I can't do that on a computer, what some books will do is, if it's the regular power gain, they'll write it like that. If I write the power gain using the decibel unit, then they'll write it like this. And you can just imagine the dB there. So this is the dB gain, and this is the power gain. Now, you might wonder why would you want to show it both ways? Well, if you remember that a logarithm is just it's an exponent basically. And remember what happens when you multiply bases, what you do, you add the exponent. So like if I had I don't know, a to the third, that's a bad number letter to use. So I had x to the second times x to the third, it equals x to the 2 plus x to the fifth. So when you're doing multiplications, you just add these. Well, it works that way with amplifiers too. Let's say that if I had an amplifier that had 3 dB gain. Now, what I can do with amplifiers, you'll learn when you take this, you can hook amplifiers to other amplifiers to get more amplification. So maybe I hook this to another amplifier, and it's 2 dB. I put that in one box. So I have a 2-stage amplifier. This one is called the front end. This is called the back end. And so the total overall gain here, I would just add these up. My total gain here would be 3, but would be 5 dB. So by having the gain as a decibel, it's a little easier to work with the math. So sometimes we'll want the regular gain, sometimes we'll want the dB gain. Just depends. Now, let's go back to the decibel unit, since you know what gain is now. I'm going to take my handout. If you didn't get a chance to print it out, you might want to just kind of refer to it if you can on your machine. I don't know if you can do that when you're on Collaborate, but I have decibel and frequency response curves, part 1. And the very first thing on the sheet is a mention of the decibel. And the definition of a decibel, it says is a logarithmic expression that compares 2 power levels. A logarithmic expression that compares 2 power levels. So here's what they do. What we do is we get the power gain. Let me get rid of this. So I deal with the power gain. So the power gain would just be the output power divided by the input power. So that would be the power gain. But now, if I want to change that to decibel power gain, so that's dB now, the dB unit, what I would do is take 10 times the log of the regular gain. So if you're writing this down, that's the very first thing you want to remember. That to go from a regular gain to a dB gain, if it's power, it's going to be 10 log the regular gain. Now remember what the regular gain is. It's really, if I erase this really is just P out over P in, like that. I just substituted this in for that, and I wrote it like this. So 10 times the log of the voltage of the gain, of the power gain, it's only 10 log when I'm using power gain. 10 times the log of the power gain will give me the decibel power gain. So if you want to write a little dB over there to make it make sense, then I would suggest you do that. So this ratio, this comparison of 2 power levels, the output power and the input power, and then doing 10 log of it, we'll take that ratio and change it into a decibel unit. We call it decibel power gain. Let me put that over here. All right. Now, let me give you an amplifier. Or a filter, not an amplifier. And over here, of course, would be my input voltage. Over here would be my output voltage. You know that basically that's this. Okay, so that's what's in the box over there. Now, if I wanted to, in this circuit, since power is, one way to get power using Watt's law is V squared over R. And since there's only one common R in this circuit, if I wanted to, what I could do, since I know that AP is equal to P out over P in, then that P out would really be V out squared over R. That's how we'll calculate P out in this circuit. And P in, that P in will just be V in squared over R, that common R, again using Watt's law. And since I got an expression for P out and P in, if I wanted to, I can take this expression for power gain and I can do a substitution for P out and P in. I can substitute and get the same formula in terms of voltage and resistance by doing this. I can substitute for this one. I get V out squared over R divided by V in squared over R. I got this fraction divided by this fraction. And I can use that, and that'll be my new power gain. That'll be power gain. But if you look at this, look at what I have over here. What I really have is, I got this top fraction. I got the top fraction is V out squared over R divided by this thing, the bottom fraction. So it's divided by V in squared over R. And you remember when you divide fractions, if you remember, you take the first one, you change that to multiplication, and you flip that one over. You just flip it over. And if you do that, you see that by dividing these like this and doing this, the R's go away, and what you end up with is V out squared over V in squared, which is kind of interesting. Then you go back to your algebra class. Remember your algebra class when you learned about exponents? When you learned about exponents in your algebra class, they told you that if you had, let's say you had A squared over B squared, you can just take the ratio of A to B and write that whole thing to the second power. Those are equal to each other. And so if I apply that to this, then what I get is I can take the output voltage divided by the input voltage and just raise that whole thing to the second power. I can do that if I wanted to. And so then I can come back over here and say, well, all these substitutions, I can take this and put over here and there, because we started out with this AP thing, remember? We started out with that. We got this, we did some fussing around with the math, and that widgeted down to this right here. So since AP is equal to this right here, I can erase this and I can put this quantity over here. I can say, all right, well, this is equal to V out over V in squared. And if you follow all the steps, I think that's everything we did is mathematically legal. Or valid, I guess you should say valid, not legal. But if you remember your logs, some people forget about their logs. You get good at doing this other stuff in algebra, but you forget about your logs. One rule when you're doing the log, if I have a 2 right here, if I have an exponent right here, what can I do with that exponent? Anybody? Tell me what you can do. What can I do with that 2? Come on, I know some of you are math people. What can I do with the 2 right here? Who am I looking at? Jacob, Randall, Sam, Tresser, I know you know. What can I do with the 2? I don't know if you guys can hear me.
The square root the A, right?
I can take this and I can multiply by that. I can bring it down. I keep looking up at the projector. I look at the camera. And if I bring it down, that's a fundamental rule of logs. What I'll get is A. Now, when I do that, this power gain now is a voltage gain. Well, actually, it's still a power gain. But I'm getting it in terms of voltage. So it's going to be 20 log. What is V out over V in? Well, all that is my voltage gain. So if I know my voltage gain, I can still get power gain from it by taking a regular voltage gain and multiplying it by 20. Kind of handy. Remember, if I have a 10 in front of the log, then in here I have power. See what I have over here? 10 log the power gain. What I'm saying is maybe you don't have the power gain. Maybe instead you got the voltage gain, but you still want the decimal power gain. Well, I just showed you mathematically where you can still get it if I know V out and V in, or if I know the voltage gain, I can still get the power gain. So another formula as we go through this filter analysis for you to write down is this one. The power gain is equal to 20 log the voltage gain. 20 log the voltage gain. And I think this looks nicer if I do this. I don't know about how you feel about it. And that's a decimal gain. So I can get the decimal power gain if I know P out and P in. I can get the decimal power gain if I know V out and V in, the regular voltage gain. Well, what about this? What about, let me think about how I'm going to show this next one. Let me go back to my circuit. And let me think about how I want to show this one. So if I have this, right, and I know that this is V in, and this is V out. This is my filter. And if I put a source here, let's put a source over here. Then I got current flowing into that circuit. So I'm trying to figure out how to derive this next one because I'm deriving this from just the circuit, looking at the circuit, trying to make the math make sense. And okay, I think I see it. So we can actually start from right here. If we start from right here, I said you can take the 2 down and multiply the 10 if you remember that from the logarithm. So I could write this like this, that decimal power gain is going to equal 20 log V out over V in, right? If I move the 2 in front and multiply to 10, then I have this. Now I'm looking at my diagram here and saying, all right, well, how would I get V out? How would I get that? Well, V out is the voltage across the capacitor. So V out is the voltage across XC, right? And so the way to get V out would be to take the current multiplied by XC. That current, the orange is the current, multiplied by this opposition, XC, will give me, so V out is the voltage across the capacitor for this particular circuit. And okay, I see that. Now, so how would I get V in? How would I get the V in? How would I get V in? Well, V in is just going to be the current multiplied by R plus, or actually minus JXC in polar form, right? But all that is the total impedance. That's ZT, or just Z. If I take the resistance and the reactance, that's the impedance. Now I can show that in polar form or rectangular form, it doesn't matter. Either way, if I take the current times the total opposition, that is the current times the total impedance, that'll give me V in. This will be I times ZT. Well, looking over here, if V out is equal to I times XC, and V in is equal to I times ZT, what I can do is substitute for V out and V in what they're equal to. And if I do that, what I'll get that the decibel power gain is equal to 20 log. Now, V out is equal to I times XC, and V in is equal to I times ZT. And if I do that, you can see what's going to happen. Since I have the common current through ZT and through XC, these I's right here are going to cancel out. And so what I end up with is another formula. Look at this one. This is nice. I end up with another way to get the power gain that says that if I want the power gain, it's equal to 20 log XC over ZT. XC over ZT. And so here are all the formulas I have for my filter analysis. AP prime is 20 log XC over ZT. Those 3 equations you will need. There was another equation I gave you last class. We derived it. Let's go in and review our graphs. So we'll use as an example a LPF. You know a response curve for LPF. This is F. This can be voltage. This can be current. And now you know what gain is. This can also be gain. And that gain can be the regular gain or it can be the decibel gain. This is frequency, but this scale right here is usually a log scale. So this is a log scale. And this right here is linear. This is a linear scale. But if I graph the frequency response curve for LPF, it looks like this. And the points we talk about right here, this 0 hertz, right there at 0 hertz. At 0 hertz, if I come here, one point that's important, I told you to remember, that's the point at where V out and V in are equal to each other. So what would that look like? Well, if I had the filter, and let's say I hook up a voltage source. So if I measure from this point right here to that point right there, that's VN. That's VN to my filter. And it's saying when I'm all the way over here at 0 hertz, V out and VN are equal. And I've been writing that on all these graphs, but nobody asked me why that was the case. So why is that the case? Why is it that at 0 hertz, V out and VN are equal? Let's look at it. If I come over here and I say, all right, I'm at 0 hertz, remember how a low pass filter works. If I think about filter action, XC equals 1 over 2 pi FC. If I make the frequency 0, so I take this frequency and I move it all the way down to 0, then this right here is infinite. It's basically open, like I have over here. It's open. That opposition is so big, this is an open circuit. It's like a frequency of 0 means the capacitor isn't even there. So let's say I have a voltage here. Let's just say I got 10 volts right here. If I take my voltmeter and put over here, and I connect it over here, this is where my output is, how much voltage would I read? Well, really what I'm asking is, what would the voltage drop be across that resistor? If the capacitor is an open circuit, what would be the voltage drop across that resistor? And the answer, of course, would be, well, there wouldn't be a voltage drop. It would be 0. Because back in DC, you learned from me that a resistor just laying on the table, a resistor with no current going, no current can flow through that resistor because the path from one side of the circuit to the other is an open circuit. Effectively, it's open. And you learn when we Thevenize that if I have an open circuit, if I have a resistor with no current going through it, it's just a piece of wire. It's a short. There can be no voltage drop across a resistor with no current going through it because it takes a current to make the voltage drop. And so if I imagine this to be a piece of wire, if my input voltage is 10 volts and there's no voltage drop over here, that means my output voltage is going to be the same 10 volts. That's why in the graph, we write this as 0 hertz, V out and VN are the same. Now, as I move up away from 0, that statement becomes less and less true. So this really kind of slopes down a little bit, but we kind of ignore that. That's why at 0 hertz, V out equals VN. That's one important point I asked you to remember on the graph. The point at 0 hertz, what's true is V out and VN are equal to each other. That's one point. What's the second important point? Well, the second important point is once we know what that voltage is, like we know in this case it's 10 volts, then I can take that value, multiply that value by 0.707, and what I get then is a point down here somewhere. I call that the 0.707 point. I don't know what it's really called. I just call it the 0.707 point because it sounds cool. But when I get that number, if I draw a horizontal line over, this ain't gonna work. If I draw a horizontal line over and intersect the graph, then what that's gonna tell me, if I drop a perpendicular down, it's gonna tell me a certain frequency, and that frequency is important because that's our critical frequency. Now that critical frequency gives us two pieces of information. Number one, we can calculate it. Remember we derived that last class. We said the critical frequency, by definition, happens when XC equals X equals R. And so we went through the math of, we said XC, I know what that's going to be. That's going to be 1 over 2 pi FC. And so if I'm calling that the critical frequency, I can put a C there. And then when I solve this, I get the critical frequency is equal to 1 over 2 pi RC. So that's another formula. We derived that last time. But here's another formula to put in your toolbox for my filter analysis. So let's just stick that over here. And I can calculate the critical frequency I'm doing 1 over 2 pi RC. And once you do that, and once you understand how to work with decibels, those are all the equations you need to do a filter analysis. But I didn't answer the second question. What's important about this point right here is that from this part of the curve over to here, that's called my pass band. So in my pass band, this is my pass band. So for a low pass filter, when I start here at 0 hertz, all the way over to the critical frequency, my power only decreases a little bit. Once I start right here, where it starts downhill, once I start right there, there's a name for this frequency. It's called the high border frequency. You don't have to worry about it. You get that in, hopefully in electronics, whoever teaches it. But when you get down to here, what's important is, just like in resonance, anything to over here, at that point, the power is decreased by half. So if my power was 100 watts over here, at this point, that's the half power point, it's like 50 watts. And look at how fast that power attenuates. So if I'm over here, the power is really attenuated. So that's important. That in my stop band, I want that to happen. I want the power to be really attenuated in my stop band over here. In the pass band, I don't want so much attenuation. So the maximum amount of attenuation I get is going to be down to half power, which is okay. We can work with that. So those are the important points on the graph. So this is all you really need, guys, to do your filter analysis, these equations here. Now, oh, I only got 20 minutes. I've been talking, doing the theory. I only got talking myself out of time. Look at the handout. I'm going to have to do some of this. I don't know how I'm going to do this. Well, I just have to go through it. Go ahead and look at the first 3 problems. And we're going to run out of time, but I'm going to have to do some of this in class because I got to get through this sheet. I don't want to leave you hanging in front of filter analysis, but I really wish, you know what I might do? I'm going to keep going, and if you guys got to go, just go, and we'll just record it. I'm going to work the whole sheet. And I know some of you got things you got to do at 4:30, but just take off, and you can go back and look at the recording. Let's go to our sheet, and I want you to look at the first 3 problems. We can actually do those pretty quick. Look at the first 3 problems on the sheet, and I'm going to give you a few minutes to work those. If you don't have the sheet, bring it up on the computer. But it says that the ratio of P out to P in is greater than 1. Oh, wait a minute, those aren't problems. That's a definition to read. It says that the ratio of P out to P, we already talked about this. If the gain is greater than 1, then this indicates an increase in power output. We call that a power gain. If it's less than 1, we have a negative gain. A negative gain would be attenuation. And the number 3 says the decibel gain of passive filters are always less than 1. Now think about that. The decibel gain of passive filters are always less than 1. The reason is, if I have a filter, a low pass filter, remember, if I have an active filter, I add an amplifier to it, so that gives me gain. But these filters are lossy because I got a resistor in there. So if I put in a certain amount of power, I'll get out, I put in a certain amount of power, I get power out, but my power out is always less than my power in. So I'm going to lose power, so there's no gain there. Now, look at the first actual practice problem, though. That's what I want you to do. Problem number 1 and 2, I'm going to give you just a couple minutes to do it. Now, hopefully you got the sheet in front of you. I'm going to read it just in case you don't have it. Problem number 1 says a certain amplifier has an input of 1 watt and an output of 100 watts. They want you to find the gain of the amplifier. So they want you to find the gain. I want the regular gain and I want the decibel gain. So if the input power is 1 watt and the output power is 100 watts, what is the decibel gain, the regular gain and the decibel gain of the amplifier? So go ahead and see if you can do that. All right. So I got an output power of 100. I got an input power of 1. I want to know my regular power gain and my decibel power gain. Okay, so let's get my regular power gain first. So my power gain is just equal to P out over P in. Now notice, if I take 100 watts and divide it by 1 watt, the watts are going to cancel out, and I'm left with 100. And that's a unitless number because gain is just a number that you can use to compare. It's what we call a figure of merit. So I get a gain of 100. There's no units. And we can give it units. We can give it the unit of dB by getting my decibel power gain. So how do I do that? Well, I just take my decibel power gain, AP prime, is going to be 10 times the log of the regular gain. So 10 times the log of the regular gain is 100. Somebody do the math for me and tell me what that is. What is 10 log 100?
I got 20
Yeah, 20.
decibels.
How many?
20.
20 dB. 20 dB. Every time you go up 3 dB or down 3 dB, you either increase, you double the power, or you half the power. So dBs are easy to work with. So if I go up, say 21, 22 to 23, whatever the power is, if it's 100, we'll go up to 200. There's a doubling for every 3 dB, or halving for every negative 3 dB. Does everybody see that? That's an easy problem to do. If I gave you that on the quiz, you can do that all night. Nothing hard about that one. Let's read the next one. So notice I have positive dB. This is it was an amplifier I deal with. The amplifier has gain, so I'm going to have a positive dB. But let's look at the next problem. It says now you got a filter. It says the input to a filter is 100 milliwatts. The output is 5 milliwatts. So this must not be an active filter. This is a passive filter because my output power is less than my input power. You got 100 milliwatts going in. You got 5 milliwatts coming out. Then I want you to calculate the attenuation. That attenuation is negative gain. I want you to calculate the attenuation offered by the filter. So see if you can do that one. My output power is 5 milliwatts. And my input power is 100 milliwatts. And they want to know, okay, well, what's the regular gain? Well, let's put the numbers in and see. I got coming out 5 milliwatts. I got 100 milliwatts going in. I do the math, I get 0.05. That's my gain. If I want to change that to a decibel gain, I take my formula. AP prime is going to be 10 times the log of 0.05. And if I do the math, what do you get there?
Negative 13.
We got negative 13 dB. Why is it negative? Because we don't have gain. If I have negative decibels, that represents negative gain, and negative gain we call attenuation. So the signal is decreased in power. You want a filter, well, depends. In the stop band, you really want it to decrease in power, right? But sometimes because of the resistor, they're lossy, you're always going to have attenuation with the filter. So they add amplifiers to it to build it back up and give you gain. And we call that an active filter. So the first two problems are pretty easy. Now, the one I actually want to get to, and this is the most important one, and this is, of course, when we're running out of time. But we got to get through problem number 3, A, B, C, D, and E, because when I give you a quiz, it's going to be over that one right there. Not to say the other ones won't be on there, but if you can do that, then the main part of filter analysis is in that problem and captured in that problem. I'm going to be quiet, and I want you to look at that problem and try to figure it out. Try to solve it. And again, I know some of you might have to work or you have other things you got to do. So if we run out of time, it's okay. We're recording this. Go back and look at it. But this is the problem you got to be able to work. I'm going to give you maybe 5 minutes to do the analysis. I'm going to come back and we're going to work A through E. And then that'll be it. So go ahead and see what you can do with it. I'll give you one hint when you're doing these. It really helps to work off the graph. Remember how we did the problem in the last class? We started with the graphs. Anytime you're doing a frequency analysis problem, start with the graph and remember the important points on the graph that I showed you. So see what you can do with that. And I'll be back in 5 minutes. All right, so the problem statement, it says you have a RC LPF, RC low pass filter. They gave you the resistor value 10 kilo ohms. They gave you the capacitor value 0.01 microfarad. They give you an input voltage of 10 volts peak to peak. They want you to find, they give you a list of things to find. The first thing is FC. Now, notice the voltage. That's kind of weird. Let me draw the schematic first. All right. They gave us the voltage in peak to peak. Now, normally when we do our analysis, we always wanted our voltage in RMS as a phasor. You call that large signal analysis. In engineering, electrical engineering is large signal analysis. And typically, when you do large signal analysis, your numbers are always in RMS. When you deal with this kind of stuff, small signal analysis, you deal with this when you deal with amplifiers and filters and such. They call that small signal analysis. You're going to show your voltage in peak to peak. One reason for that is when you're measuring with an oscilloscope, you don't want to have it in RMS. Well, at least for the old analog scopes. It's just easier to get a number if it's in peak or peak to peak. So it's customary to write this in peak to peak. The first thing they want us to do is find the critical frequency. That's so simple. It's just that formula. So everybody should have got that one. The critical frequency is 1 over 2 pi RC. It's going to be 1 over 2 pi. I got 10,000. I'll leave off the units. And I got 0.01 times 10 to the minus 6. Again, I'll leave off the units. So everybody should have got that one. What do you get for the critical frequency? Anybody?
I got 1,592 hertz.
Is it hertz or kilohertz?
It would be like, I think it would be like 1.592 kilohertz. So I think it was, I think I got 1,592
Yeah,
hertz.
1.592 kilohertz.
Okay, so then it's hertz. All right, so now I want you to work off the graph. Okay, so work off the graph. So let me see here. Where's my purple? Right here. So let's make a graph. And what I know so far about the graph is it's a low pass filter, so I know the response looks like this. And I don't know, I know this point right here, don't I? That's the point where Vn equals V out, so I know that point. And now look at what else I know. That's FC. So if I go down to this point, that's my 0.707 point, and I come over here, I intersect and drop down, then I know that that point right there is 1592 hertz. 1.592 kilohertz. Okay, so that's what I know. All right. All right. so that's A. Now B, look at B. B says, let's find the decibel gain, the decibel power gain. All these are power gains at 0 hertz. What would the decibel power gain be at 0 hertz? How would you figure that out?
You would do just 10 log of 1, right? It should be 0.
Yeah. Excellent. Here's what he's saying. Look. Now, this might help if I do this. Remember this right here? That right there, AB is V out over V in. So if you think about it like that, that might be better to write these. This is really V out over V in. And this one is P out over P in. So what Jacob is saying is, if I look at my graph, I realize that at 0 hertz, that's right there. What can the graph tell me about 0 hertz? What it can tell me is that's the frequency at which V out and V in are equal. Now we know what V out and V in is for that at 0 hertz. It doesn't even matter. It doesn't matter. All that matters is they're the same value. And so what Jacob said, well, if this value and this value are the same, then this gain is going to equal 1. So if I take this formula right here and put a 1 into it, then that's going to give me my answer. I'm going to have AP prime is going to be 20 times the log of 1. And if you do 20 times log 1, what do you get?
You just get 0.
You get 0? You get 0 dB?
Yeah.
Okay. Now, don't be bothered by a 0 dB. 0 dB it's not the starting point. It's like if this is, let's say this was 0 dB, then I can go down to this. Oh, you know what? Two things. I didn't say this. If I look at this, remember I said this axis can be in gain. This will help you out. This axis can be VI or it can be gain, power gain, right? Well, that 0.707 is also called the 3 dB point, the 3 dB point. In other words, this point right here is always 3 dB down from that top point. So here's what I'm trying to say. If I have a graph and I tell you that that point where V out is equal to V in, let's say that that point is 100 dB. And the 0.707 point right here is always 3 dB down. It would be 97 dB. Remember I said that for every 3 dB, you lose half the power? Well, it works right here. If I go down 3 dB, my power is decreased by half at that frequency. Now, for this, we got 0 dB. If I start this at 0 dB, then that 0 is just a reference. This will be down, and I can go down here. 0 minus 3 will be a minus 97 dB. So that starting point is just kind of a reference. All right, so you got 0 dB, and that's our decibel gain at 0 hertz. Well, look at C. Look at C. I kind of already gave you the answer to it, but look at C. C says, give me my gain at 1.592 kilohertz. What is 1.952 kilohertz? What is that?
That was the critical frequency.
That was a critical frequency. They want a decibel gain, and I just gave you the answer to it, but act like I didn't do that. We had to figure it out. How would I find the decibel gain at this point right here, at the critical frequency, is what they're asking. So if I go back, that would be over here. Well, I know what that is. Right here, that's that 0.707 point. Right? That's the 0.707 point. What do I know about the 0.707 point? What do I know about it? Well, I know that the voltage is 0.707 of the total voltage, but what else do I know? I know that that's the point at which the power is what? Decreased by half. So what you could do is this. In my tools over here, I can go right here. The power gain. Now I haven't calculated any powers. I don't know what the powers are. All I know is for my power gain, all I know for my power gain is that P out over P in, all I know is at that point that ratio is equal to what? 1/2, which is equal to 0.5. So without knowing my input power, without knowing my output power, I know that the power at that point right there is half my total power. So I kind of know something about this number right there. That at the half power point, the 0.707 point, the power ratio is equal to 0.5. So all you got to do is take that 0.5 and put it in here, your answer. So if I say AP prime is equal to 10 log 0.5, what do you get now?
-3.
Yeah, -3.
Negative what?
3.
Negative 3 dB. Well, does that make sense? It does make sense because you told me in my graph that right here, that level right there, you said that was 0 dB. So if I go down to the half power point, it's going to be 0 minus 3. That's negative 3 dB. It's 3 dB down. So this is adding up. But notice how we didn't have to do any calculation with the actual P out or P in. I got my answer. Minus 3 dB. Does that make sense? Well, it kind of does because remember, we're not dealing with an amplifier. Amplifiers have positive gain. This is a filter. There's negative gain, but negative gain is called attenuation. So the 0 dB and they don't bother me at all. I expect that from a passive filter. Now, they're trying to get you with C. Look at C. I mean, not C, but D. They want you to find the decibel power gain at 15.9 kilohertz. Look at that. In other words, look at my graph. If this is 1.5 kilohertz, I don't know where 15.92 kilohertz is, but it's way out here somewhere. And so I expect when I go up on this graph, if this is the point, look how my signal's attenuated, way over here. So I expect to have a I expect to have a lot of attenuation there. That's what the graph says anyway. Let's see if the math agrees. See if you can figure out D, and then figuring out D, we already did E. E is right here. They want you to sketch the graph, put the values in. We've already done that. So if you can figure out D, we're done. D-U-N, done. D-U-N, done. Okay, see what you can do with that one. Guys, I hope I wasn't gone too long. I see you guys were signing off. But I had to take a phone call. So we will, oh, you guys are. So we will, there's a couple ways you could do this problem. But if you're kind of following the logic of the problem, first we use this equation, then we use, I think, this one, and then this one. So now we're going to use this equation. There's other ways you could do it, but what we know is they gave us the frequency. They said that our frequency out here was 15.92 kilohertz. Since I know that, then I can easily find XC, which would be that. If I have XC, since they gave me R, I can find that. Then I can use that equation to solve for my power gain at that point over there. So this is not the only way to do it, but just kind of following the logic of the problem, I'm going to go ahead and do it that way. So this is going to be 1 over 2 pi FC. So if I put my numbers in there, it's going to be 1 over 2 pi. The frequency is 15.92 times 10 to the third hertz. And my capacitor value is 0.01 times 10 to the minus 6 farads. Again, I'm leaving my units off. So if you have your calculator, I don't have mine handy, but if I have to get it, I will. Somebody give me the value of XC at this frequency right here. What would that be?
I got 999.7.
Yeah, I got the same.
Okay.
We're going to just round that to about 1,000 ohms. Okay? Well, if we know that's 1,000 ohms, then I guess I can erase some of this. Let's figure out, that's this number. All we got to do is get the denominator, ZT, and we're good to go. And you know from other lectures that ZT is just going to equal R squared plus XC squared, square rooted. And so if I take my R, which is 10,000, and I square it plus the 1,000, and I square it, take the square root of it. Well, think about that triangle. That triangle looks like this. I got this long side right here, which is 10,000, and this short side right here, which is only 1,000. So that's the triangle right here. So I expect the hypotenuse to be real close to value as my R value. So when you do the math, I'm expecting something really close to 10,000 from that triangle, that right triangle. So what do you get when you do the math here?
I got 10. I got 10K. So yeah, 1,000, 10,000.
Okay, so we'll just go with that. So you got 10K.
10,050. It was really close.
10,050. Okay, so we can put that in there, 10,050 if you want. But if I do the math here, so let's do 20 log. If you want to do, what we say, this was 1,000, and this was something like that. Or you can use 10,000. It's not gonna matter. That 50 is not gonna matter. So what do you get when you do the math?
I got negative 20 decibels.
Okay, now think about what that means. Remember we said that for every 3 dB, the power is halved? So I don't know what the power was here, but it's halved here. If I go all the way down to here, negative 20 dB, that power is, I mean, you can't hear that. I mean, that signal is attenuated so much it's dead in the water. Dead in the water. So that is a basic filter analysis using a low-pass filter as an example. And so at some point, you got to show me that you understand what we did here. So that's it. If I gave you part 2, it's kind of more of the same. We do talk about another concept. I'm not going to get into it, but I think we're just going to stop here with this. Now, I was walking to the restroom a little second ago, and I thought about something. not exactly with filters, but we talked about bandwidth. It just hit me while I was on my way down the hallway, and I was trying to explain the importance of bandwidth. One example we have right in front of us is this camera. Remember, I was at home in my basement, and I kept saying that you guys got to mute your microphones when you're not talking. You can't have your cameras on. I said my bandwidth is too low. And you can probably tell the difference in the video quality, too. I think I went back and I replayed the video. The ones in my basement where the bandwidth is low, real grainy. The ones here is almost like high definition. In the basement, sometimes I would move my mouth and the words would come out a few seconds later. The bandwidth was just terrible there. Here I have a lot of bandwidth, and since nobody's in the building, I got the whole Cincinnati State, basically almost the whole Cincinnati State internet bandwidth. There might be 5 people in the building using it. I don't know what the number is, but it's really low. So you can see a difference in the quality of the picture, my voice, and everything. It all has to do with bandwidth. The bandwidth here at the school is huge compared to what I have at home. And you can just tell a practical example of a high bandwidth situation and a low bandwidth situation. You can actually see with your eyes. So that's a good example of that. Well, guys, I thank you. It looks like Jacob and Sam, and I think Randy just left. Thank you for sticking with me later. So that's it. That's all I have. Do either of you have any questions before I sign off? Any questions or comments? Well, if you don't, what I need for you to do is, as I said to the rest of the class, I'll be communicating with you, since I won't see you before Monday. I'll be communicating with you through Blackboard, and I'll see you guys on Monday up at the school, and I'll be sending out some information to tell you how to prepare for that. Other than the mask right now, I don't know what to tell you to bring, so have a mask available. And if there's anything else you need to know, I'll make sure you get the information either today or tomorrow. Thank you for sticking with me. Thank you for doing the calculations, and I'll talk to you guys on Monday.
All right. See you.